and I'll get the share screen going. Now, before I start, are there any questions about what happened last time that people would like to ask? Anything? All right. Well, if not, we can go ahead and start. So the plan today is to finish the second proof of the theorem that we started from the beginning. We were handed a set of parameters and a certain indiscernible, or sorry, we were handed a set of parameters and a sequence, and we wanted to find an indiscernible sequence that somehow closely resembled that sequence, namely that it realized the EM type. And the first proof that we had of this was using Ramsey's theorem. And the second proof that we're going to give involves invariant types. And invariant types are like a really ubiquitous model-theoretic tool. So it's important to see sort of how they work, and this is like a nice theorem to prove with them. But we're going to use them just all over the place, so that's really the point. So let's just recall what we did last time. So last time, we defined invariant types. And let's just recall the definition. So you say, so I'm gonna give a definition which is slightly more general than what I did last time. So let's say, suppose you have a model N which contains A, and N is A plus saturated. So it can realize types over A. That's the main thing. Then a type P in Sx of N is A invariant if for every formula phi xy, which has possibly parameters from A, and B and C from N, with B having the same type as C, we have that the type is all that determines membership in the type P, not actually the identity of the element. So we have that phi xb is in P if and only if phi x c is in P, and this is equivalent to sigma of P equals P for every, this is just a comment, for every sigma in the group of automorphisms of N fixing A pointwise. Okay, now the reason that you need this sort of saturation hypothesis is just to get this equivalence. Because if you don't have a saturated model, then it could be, for example, rigid. It could have no automorphisms. And then every automorphism that that you take will fix the type, of course, but that doesn't mean that somehow the information of whether or not a formula goes in the type or not is determined only by the type of the element. So some saturation is important for this to make sense. But normally, what we do is we immediately restrict the case when N is the monster. So we normally consider the case when N is equal to the monster model. Why? Well, here's an observation, which I think gives some sense of like how this thing goes, which is suppose N is cardinality of A plus saturated, and A is contained inside of N, then if P in Sx of N is A invariant, then P extends uniquely to a global A invariant type Q. So that'll be an Sx of the monster model. Okay, now let's think about why. Well, the type of an element over A should determine whether or not formulas go into the type or not, right? Now, every type that you could possibly write down over A will be realized in N because N is sufficiently saturated. That's what saturation means. So if you have some formula in, the monster model, so you have parameters coming from the monster model, and you want to know, should I put it in my type or not? You just realize the type of those parameters in N, which you can do by saturation, and then you look and see if that's in the type or not. And if it is, then you put it in, and if it's not, then you don't, and that tells you how to build an invariant type. So let me sort of say this again, sort of by a picture. So here we've got the monster model. We've got our small set of parameters A. This is the set over which we want to be invariant. And then we take some submodel N. And the proof is just, we're going to assume that we're given P, which recall is in Sx of N, and it is A invariant. And what we'll do is we'll define Q to be the set of phi x c. So phi will range over all formulas in L of A, and C will be an element of the monster model, or a tuple from the monster model. So this is like in m to the y, such that there is some b in N which has the same type as C over A, and phi xb is in P. So here I've got C, and I'm looking at this formula phi xc, and I want to know, does it go in the type or not? Well, C will have the same type over A as some guy B living inside of N. Now I want my type to be invariant. So the question of whether or not I put phi xc into the type is the same as whether or not I put phi xb into the type. And P is in Sxn. It's complete over N. So it definitely will make a decision about whether or not phi xb goes in the type or not. And so that determines a complete extension to the monster model. So something that I leave it for you to check, it's an easy argument, is that Q is complete, consistent, and A invariant. So complete and invariant are sort of obvious from the definition. Every formula is going to be in or out, but consistency takes a small compactness argument, and this is where you use invariance. So I encourage you to try it if you want some experience working with these. But in any case, the point is, if you know it for one sufficiently saturated model, then you know it for all of them. So you might as well work with types over the monster because they're somehow uniquely determined once you've gone to a big enough model. Okay. So this explains why normally when we work with invariant types, we work with global invariant types. We just assume that we've extended them to the monster. All right, so what I want to do now is I want to describe a certain operation on invariant. Yeah.
I have a question. Yeah. So how did we find this B inside of N? Are we assuming that N is saturated at all?
Yes. So that was part of our assumption. So the observation said assume N is A plus saturated. And you're exactly right. If we didn't have that assumption, then this argument would not work, because the reason that we can realize, so the point is that we look at the type of C over A, and this can be realized in N. By saturation, and the realization is what we call B.
Okay. So we're sort of going from one monster to another then, right? Or
yeah, but okay. The monster model is like bigger than everything in sight, right? Like you sort of secretly assume that the monster model is like a strongly inaccessible cardinal in size, right? Now, how big do you need to be A plus saturated? Just 2 to the A plus or something, right? So I mean, you're right. From the perspective of A, n might as well be a monster model, but from the perspective of what we're doing, it might be still pretty small. So there's a real difference between these two things. So the point is just that like once you see all of the things that A can see, namely once you've realized all the types over A, you've determined all of the information that an invariant type can know, and that's bounded. Whereas like the size of the monster model is from our perspective unbounded. So it's just, this is another way of sort of highlighting the fact that invariant types have some kind of compression. They're determined by a relatively small amount of information. Right. Okay. Any other questions? Okay. So now I want to define the tensor product on invariant types. All right. So suppose P, let's say, yeah, okay. So let's say P is in Sx of the monster model, and Q is in Sy M of the monster model, are global A invariant types. So I have two global invariant types, which are maybe in different variables. And what I'll do is I will define, and the definition is a bit strange. So let me tell you what it means. Define the type P tensor Q, which will now be in the variables of each. So it's in the variables xy, to be the type A, B over the monster model. So it's a global type for some B, which realizes Q, and some A, which realizes P restricted to M over A. And immediately you should say, this makes no sense. This makes no sense whatsoever. Why does this make no sense? Well, first off, we have a convention in place that everything that I mention should be inside the monster model. So when I realize a type, where is my realization? It's inside the monster model. So how can I realize all of Q? I mean, Q is a type over the monster model. I probably can't realize it inside the monster model because one of the things it probably says is that I'm not equal to any element of the monster. Then P, to make matters even worse, P is a type over the monster model, and here I am realizing it over M restricted to A. That's not a restriction, that's an extension. So this seems to make no sense at all. But it kind of does make sense, because what we saw is that once I know how to extend my type to an n plus saturated model, I know how to extend it arbitrarily to whatever I like. So there are two ways of doing this. One is you can work in a second monster. So you can extend the monster further, find your A and your B, look at the extensions. Or what you can do is you can sort of fix, so this was cheating. So what you can do is instead fix some n that contains A, which is A plus saturated. Realize Q restricted to n, and A will realize P restricted to n over A. Then what you can observe that the type of A, B over n is A invariant, and let P tensor Q, which is now in Sxy over the monster model, so this is an extension of the monster model, be its unique A invariant extension. So the picture here is this is a way of doing it without cheating. So we've got the monster model, we've got A, we pick N, which is saturated relative to A, and we've got these two types, P and Q. So first I realize Q over N, and then I get some bigger set, which is N together with B. Sorry. Here I wrote in A, but I really meant in B. It doesn't make sense to realize A over in A. And then over B, I realize A. So this is in B, over the realization I picked. So first I realize Q, and then over the realization, I realize A. Okay, so let's check that this actually does define an invariant type. So that this argument makes sense. So why should this define an invariant type? So claim this defines an A invariant type. Now let's recall what we have to prove. What we have to prove, so we want to show that if phi x, if phi x comma y, let's say z, is a formula possibly with parameters in A, and let's say we have C and C prime, which are, sorry, oh no, that's not how it's supposed to happen. I should probably silence all of my text messages. Okay, so these things are in N, and C is equivalent over A to C prime. What do we want to show? We want to show that phi x, y, c is in P tensor Q, say over N, if and only if phi x, y, c prime is in P tensor Q restricted to N. Okay, this is what it means to be invariant. If we take two things that have the same type over A, then one goes in the type if and only if the other does, right? Okay, now, so how do we do this? The first step is we note that if, so let's do it this way. So the first thing we want to note, so note, oh no, what's happening? So note, if B realizes Q restricted to N, and C has the same type over A as C prime, C and C prime are in N, then C and C prime have the same type not just over A, but also over AB. Why? So let's think about why. This will use the invariance of Q. So suppose you have some formula, C, which is, let's say, CB. So C here will be a formula in LA. So I take some formula and I want to say, I know that C satisfies it. Well, that happens if and only if CY is in Q restricted to N. Recall that C came from N, so it's okay. It's restricted to N, we still have this. Now, Q restricted to n was invariant. So this happens if and only if C of C prime y is in Q restricted to n. So this is the part where we use A invariance. And then this happens if and only if C prime B holds. Okay, so what does this say? This says if I take an arbitrary formula with parameters A, B, then it's going to be true of C if and only if it's true of C prime. So that establishes that C and C prime have the same type, not just over A, but also over AB. Okay, so that is good news. Then we recall that A realized P over NB now, by the above, we know that BC has the same type over A as BC prime. That follows from C and C prime having the same type over AB. So again, by invariance, we have phi x BC is in P over NB if and only if phi x BC prime is in P restricted to NB. Because they have the same type. But A realizes this type. So we have phi A BC. Oops, that should be a C. If and only if phi A B C prime, i.e. phi x y C is in P tensor Q restricted to N if and only if phi x y C prime is in P tensor Q restricted to N. I ran out of space there, but you know what it says. Okay, so what's the idea? The idea is if I use in two steps invariance, I know from the first use of invariance, the fact that Q is invariant, I get this fact, that not only does C and C prime have the same type, but BC and BC prime have the same type. And that puts me in a position where I can use the invariance of P to say that then AB will realize a formula with C if and only if AB realizes the same formula with C prime. And that's what it means for the type to be invariant. So this shows, oops. So P tensor Q restricted to N is a invariant. And that was the goal. Now, as we observed before, it's enough to show that it's invariant over some small model, because then we've defined it really to be the unique A invariant extension of that type, the restriction over this. Okay, is this clear? So this gives us a way of putting two types together. Now, one comment, connection back to ultrafilters. So I don't know, has anyone seen the tensor product of ultra filters? Is that a thing you guys have seen? No. So, okay, so here's a cool fact. If you take an ultrafilter on X and an ultrafilter on Y, you can put them together and get an ultrafilter on X times Y. And how do you do that? So suppose X, well, let's just say it this way. Suppose that you have D, which is an ultrafilter on X, and E, which is an ultrafilter on Y. Then D tensor E is an ultrafilter on X times Y, defined so that you have an arbitrary Z subset of X times Y and this satisfies the stipulation that Z is in the ultrafilter if and only if whenever I look at a pair or let me say it this way. Whenever I look at the X in X, such that the set of Y, such that X, Y is in Z, is in E, that's in D. And this is really hard to parse the first time you see it. So let me draw a picture because then I think that clarifies things. So we have this pair of axes. Here's X and here's Y. And then we've got some blob living inside this space, which is Z. And if I fix an X down here, I can look at its fiber, like the points above X, and I can ask, where do they intersect Z? So if we look here, we see like this is the points sort of in Y, or, you can identify it with these points in Y that sort of live above X. And you can ask, is this big or is it small? Now, for some of the fibers, maybe you have a big set, and for some of the other fibers, maybe you have a small set. Now, a set Z will be considered big in D tensor E if and only if the set of X's such that the fiber above X is big with respect to E is big with respect to D. So for D many X's, you have big fiber, where big fiber means big with respect to the ultrafilter on Y, E. Does that make sense? Okay, now you'll notice that this is not commutative, and it's rarely commutative, but it is associative. So this is like an associative operation on ultrafilters, and there are a lot of things in combinatorics that use this structure on ultrafilters. You have this product operation. You can try to take idempotent ultrafilters and use them in Ramsey theory. Now, one thing that is interesting to observe is the following. So, observation. Suppose I have P, which is in. Oh, sorry. Let me get out really quickly 1 second because my screen is starting to lag again, and I've had good luck just stopping and starting again. I'm going to try that. So let me do share screen one more time.
And Nick, the other tensor product we defined for types, that is not commutative either, right?
It's not commutative either.
Okay.
Although in certain cases it will be. And you know, somehow the special case of types, when you have types that commute, that says something, that it means somehow that you're close to stable. And that's a hypothesis that we'll sometimes see, that you have types which commute. Okay, so let's consider the relationship between the operation on ultrafilters and the operation on types. So suppose you have two types, S xm and q in sym, which are not just A invariant, but they're in fact equal to averages in the sense that we defined before. So P is going to be the average of, say, D over the monster model. Q is the average of E over the monster model. And D and E are ultrafilters on A. So let's remember the setup. These average types were defined last time, and what was their definition? You just say a formula goes into the ultrafilter, or sorry, it goes into the average type. If whenever I look at the elements of A that satisfy that formula, that is a large set with respect to this ultrafilter. So you have a set A, which is probably small. So here's A, and you take an arbitrary definable set, so phi x c, and this definable set will go into type just in case this intersection is large with respect to the ultrafilter that you're given. So this is the average type. And we established last time that this always defines a complete type, and it's always invariant over the set on which the ultrafilter is defined. So if our ultrafilter is on A, then this produces an A invariant type. Cool. So the observation, which I think kind of intriguing one, is that if I take this tensor product of types, this is just equal to the average of D tensor E over the monster model. So this generalization of types, I mean, this is sort of explains the choice of notation. This tensor product of types comes from the tensor product of ultrafilters. Now, I don't want to mislead you. There are lots of invariant types that do not arise from this construction. So you can be invariant without being an average along some ultrafilter. But when you are of that form, then this tensor product of types really does match with the tensor product of ultrafilters. And this observation is really just chasing definitions. So I encourage you to try to do it. So I'll leave that to you. Okay, so now let's go back to our goal of trying to prove that if I'm given a sequence and a set of parameters, I can cook up an indiscernible sequence that realizes the EM type. All right, so what we'll do is first, let's just make a really easy observation. So suppose D is an ultrafilter on omega. Then if I look at the set of I in -1, I in -2, dot, 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 all the way down to I0, such that I0 is less than dot, 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 less than IN -1. This is in D tensor dot, 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 tensor n times. Okay, let's think about why. So let's do this for 2, and then it'll sort of be obvious why. So let's restrict ourselves to showing that if we, so just give the proof by example. So let's consider this, that this is in D tensor D. And for this to be true, let's say it's non-principal. This is one time that I actually think we need that hypothesis. Okay, why? Well, what do we have to show? We have to show that the set of I such that the set of J such that J is bigger than I is in D. Right? So if I fix a particular I, here's omega, then I split the world into two halves. I have the points which are outside the set, which are the points less than or equal to I, and then I have the points which are inside the set, which are the points which are greater than I, which are out here. Now, one of those is finite, because one of them is the natural numbers less than or equal to I. There are I of those, or I guess I plus 1. And the other one is infinite, which is the numbers bigger than I. And assuming that our ultrafilter is non-principal, exactly one of those can be in the ultrafilter, namely the big one, right? The infinite one. So for any I, this is true, right? If I take I, no matter what I is, the initial segment up to I is finite, and the in segment above I is infinite. And so always the in segment is the one in the ultrafilter when the ultrafilter is non-principal. So this set, I mean, this condition is just always satisfied. So this is actually just equal to omega. So this is clearly always in the ultrafilter. So that establishes this. And then it's easy to generalize this argument by induction. If I fix an in tuple of numbers, then the in plus first element will always be bigger than the initial segment determined by that in tuple. Take the max of those numbers, you're always going to be bigger than all the others. So it's easy to see this fact. And this is really all we're going to need to prove the theorem. So let's prove the theorem. So let's just recall the setup. So suppose A is a set of parameters and I, which is I less than omega, is a sequence of tuples of the same length. Then there is an A indiscernible sequence J that realizes the EM type of I over A. Okay, and again, this is something we've already proved. We're just doing it again in a different way. So what do we do? So the proof, obviously we want to use average type somehow. So what we're going to do is we're just going to fix a non-principal ultrafilter on our sequence of tuples. So let D be a non-principal ultrafilter. On I. And now let's remember what we get. What we got in what we said before is if I look at the average of D over the monster model, that will be invariant over which set? It's invariant over the set on which the ultrafilter is defined, which is to say it's invariant over I. Now, we needed indiscernibility not over I, but over A. And that seems like a problem. But what we can do is we can realize our type not over I, not over A, but over AI. Now, it's easy to check that invariance over a small set implies invariance over a big set, right? Because if I know that whenever two elements have the same type over, say, a small set A, then the decision of whether or not the formula goes in is, there's no difference. Then, of course, if two elements have the same type over a bigger set, then also one will go in the type if and only if the other goes in the type. So invariance over a small set implies invariance over a big set. So even though the argument that we had before says that the type av d m will be I invariant, it's in particular also AI invariant, and then that's what we'll use. So we will choose a sequence J, which is bi I less than omega, such that J, or let's say it this way, such that bi realizes the average type of d over a, I, and everything that came before. So let's draw a picture. Here we've got the monster model, we've got our small set A, we've got our sequence I that we want to look like. And basically we first realize B0, and then over all of the stuff we realize B1, and then we realize B2, looking more and more and more like the sequence I. Okay, so this sequence is J. Cool. So what do we know? So by last time, we know that J is AI indiscernible. Because we proved that if you're an A invariant type and you realize a sequence in this iterative way, then you produce an indiscernible sequence. It's a way of generating an indiscernible sequence. Since our type is not just A invariant, it's also AI invariant, we can generate this type over AI, generate the sequence over AI, and then that'll produce an AI indiscernible sequence. But if you're AI indiscernible, then of course you're indiscernible over any smaller set. So J is A indiscernible. Great. So it at least is an indiscernible sequence. Now we just need to prove that it realizes the EM type. And for that, we just note that by definition, we have that Bn minus 1 through B0, let me write this on a new line, realizes the average type of D tensor dot 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 tensor D, this is n times, over A. I mean over AI, but in particular over A. Why? Well, notice that the order switches, and this is a little annoying, but when we defined P tensor Q, we first realized Q, and then we realized P. And so here, when I've defined my sequence, I first realize the type, and then over that realization, I realize B1, and then over B0 and B1, I realize B2, and then over B0, B1, B2, I realize B3. So the order is going from right to left, unfortunately, but okay. We can deal with that. And what do we know? We know that if phi, let's say x0 through xn minus 1 is in the EM type of I over A, then the set of all A 0 through AI in minus 1 such that phi AI0 AI in minus 1 is true, this has to contain all AI0 through AI in minus 1 such that I0 is less than dot 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 is less than I in minus 1. That's just the definition of EM type. A formula goes in the EM type if and only if whenever I take an increasing in tuple, the formula is true. So I have to contain all of these things. Right? And then where do we go from here? Then this set with the order reversed, let's say A I in minus 1 through A0, AI0, I0 less than dot 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 less than I in minus 1. These are just the tuples that I take where the indices all increase or actually decrease in this order. This is in D tensor dot 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 tensor D by what we said before. If I just look at increasing in tuples enumerated in reverse, that is always in this tensor product of ultrafilters. So phi x0 through x in minus 1 is in av d tensor dot 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 tensor d over A, where the variables, remember, go down, which is realized by b in minus 1 through b0. So we have b0 through b in minus 1 makes it true. Okay, so this is a bit annoying because of this order switch, but it's not too complicated. What we're saying is if I have a formula which is the EM type, then I know no matter which increasing in tuple I take, the formula has to be true. And that means that the set of increasing in tuples where it's true is large with respect to this ultrafilter, this tensor product of ultrafilters. Now this type, the average type determined by an n-fold tensor product of ultrafilters, is realized by the sequence that I generated, b0 through bn minus 1. And so the formula in the EM type is certainly contained in the type of b0 through bn minus 1, which means that the EM type is realized. So what does that do? That says that I start with my sequence, I take an ultrafilter in the sequence, which tells me something about the generic behavior on the sequence. It makes a decision about all of the formulas where things change. So this is how you should think about it, right? So if I take a sequence, which is not indiscernible, then some of the behavior is constant and some of it changes. And what I'm using is I'm using this ultrafilter to make a decision about the stuff that changes. So anytime something changes, I have two choices. I can make it true or I can make it false, and the ultrafilter will say, do I make it true or do I make it false? Now, of course, anytime that something is true always, the ultrafilter will not disagree. It'll just say, yeah, the places where that's true is big because it has to be, it's everything. And as a consequence, using this ultrafilter, you find a new way of generating your indiscernible sequence, which avoids the use of Ramsey's theorem. Now, the difference between these two techniques is not so big because, of course, you can prove Ramsey's theorem using ultrafilters. And the proof of Ramsey's theorem using ultrafilters can secretly tell you why these two proofs are more or less the same. But something that's very intriguing to me is that very soon, in fact, starting in, I guess, Monday next week, we'll start worrying not just about indiscernible sequences, but indiscernible trees, indiscernible random graphs, all kinds of new structures. And then this connection between a proof where you generate a sequence using a global invariant type, and this proof using Ramsey's theorem, these don't seem to talk to each other anymore. And it would be very interesting if there's a way of unifying these. That would be a topic for research, not for this class. All right, so I guess that's all I want to say today. I will stop the recording. But are there any questions before we end?
So when you said